All right, today we're going to unravel something that's so fundamental to our daily lives, we pretty much just take it for granted. I'm talking about weaving. You know how simple thread gets turned into all the fabric around us? It's actually a mechanical marvel, like this high-speed symphony of perfectly timed movements. So let's dive right in.
No, really? Just for a second, look down at the clothes you're wearing right now. Your shirt, your jeans. How in the world does something as weak as a single thread become this strong, complex fabric you can wear every day? Well, the answer is all in the absolutely incredible engineering of the loom, a machine that's been perfected over thousands and thousands of years.
Okay, so to really get how this works, let's try an analogy. Don't think of a loom as just one machine. Think of it more like a tightly coordinated orchestra. Every single part has a super specific job, and they all have to work in perfect harmony. So let's go ahead and meet the key players in this orchestra.
First up, we've got the warp threads. Now these are the unsung heroes. They're the lengthwise yarns that are stretched super tight, right from the back of the loom all the way to the front. They are the absolute foundation, the backbone of the fabric. They provide all the strength and stability.
All right, so if the warp is the backbone, then the weft, well, that's the thread that brings the whole thing to life. The weft, which is sometimes called the filling, is the yarn that actually moves. It travels from side to side, weaving in and out of those warp threads to build the cloth and create the pattern you see.
So you might be wondering, how exactly does that weft thread get in between all those tight warp threads? Great question. And the answer is heddles. Picture this. Every single one of those warp threads is threaded through a tiny eye in something called a heddle. By lifting certain groups of heddles, the loom can lift specific warp threads. And that is absolutely crucial for what comes next.
And here you can see how it all fits together. It's a perfect illustration. See that big beam at the back? That's the warp beam. Then in the middle, you've got the heddles doing their job, controlling which threads go up and down. And then right at the front, that's the finished cloth being wound up. All these core parts are about to perform this unbelievably fast and precise dance.
You know, when you really get down to it, all of weaving, no matter how complex the fabric, boils down to just 3 basic motions. That's it, just 3. They're called the primary motions, and they repeat over and over again, hundreds, sometimes thousands of times every minute in this perfect high-speed cycle. Let's break down this little 3-step dance. Okay, here they are. Shedding, weft insertion, and beat up. Simple as that. Without these 3 things happening in order, you can't make fabric. It's impossible. So let's take a look at each one.
So step 1 is called shedding, and this is where those heddles we just talked about get to work. Remember them? By lifting up one group of warp threads while leaving the others down, the loom creates this V-shaped opening, kind of like a little tunnel, and that opening has a name. It's called the shed.
Okay, so now that we have that shed open, it's time for step 2, weft insertion. This is pretty straightforward. A weft yarn, and each one is called a pick, is passed right through that V-shaped tunnel, traveling all the way from one side of the fabric to the other.
And, there are a bunch of different ways to get that weft thread across. The really old-school looms used a wooden shuttle that literally flew back and forth. But today's modern, high-speed looms, they're shuttleless. They use things like projectiles, or these cool metal arms called rapiers, or even powerful jets of air or water to just shoot the yarn across in a split second.
And that brings us to the final primary motion, and it's called the beat up. Sounds pretty aggressive, right? Well, once that weft yarn is all the way across, this tool that looks kind of like a giant comb, it's called a reed, swings forward with a lot of force, and it pushes that new piece of yarn, that pick, firmly up against the edge of the fabric that's already there. And yeah, that name beat up is definitely not an accident. There's a quote from our source material that explains it perfectly. It says, "The pushing of the yarn is done in a harsh manner." I mean, it takes a ton of energy to pack that new thread in there really tightly, locking it into place and making sure you get a dense, strong piece of cloth.
This diagram here gives you a perfect view of that beat up in action. You can actually see the reed. See those individual metal strips? It's combing that weft thread into the rest of the fabric, really compacting the weave. And as soon as that's done, what happens? The whole cycle starts right over again. Shed, insert, beat up. Over and over and over.
But wait, for this 3-step dance to just keep going without ever stopping, you need a support team, right?
You need a stage crew working behind the scenes, and that's where the secondary and auxiliary motions come in. Their job is to make sure the whole process is continuous, efficient, and that the quality is top-notch.
So there are basically two types of these support motions. First, you have these secondary motions. Think of these guys as the ones who keep the show running. Warp let-off is slowly feeding new thread in from the back, and fabric take-up is winding the finished cloth at the front. They make sure the performance never stops. Then you've got the auxiliary motions. These are your quality control and safety crew. Their whole job is to stop the loom instantly if a thread breaks, which prevents flaws and makes sure the final product is perfect.
So, who conducts this whole mechanical orchestra? Well, it's this, the crankshaft. Just like a conductor's sheet music, the rotation of this one main shaft dictates the exact timing of every single movement in the loom. The entire cycle is mapped to the 360 degrees of that crankshaft's turn, making sure the shedding, the insertion, and the beat-up all happen in perfect split-second synchronization.
Okay, so now let's look at how this whole thing comes together. Because designing a loom isn't just about making these motions happen. No, it's about fine-tuning them to create a very specific kind of fabric, all while balancing these unbelievable speeds with just immense mechanical forces.
And this is where we get into some seriously clever engineering. I mean, to make everything from a light silk scarf to a heavy pair of jeans, engineers have to tweak the loom's every single move. One of the key ways they do this is with something called the sleocentricity ratio. Don't worry about the name. It's basically a calculation that adjusts how the reed moves, fine-tuning the rhythm and the force of that beat-up.
And if you look at this table, you can see this is not a one-size-fits-all deal. A loom made for weaving delicate cotton might have a low ratio, like 0.23. But then you look at a heavy-duty loom that's making thick industrial blankets, and its ratio is way higher, at 0.54. So what gives? Why the big difference?
Well, it's all about timing and force. A higher ratio makes the reed, that big comb, pause for just a fraction of a second longer at the back of its swing. That gives more time for the weft to get all the way across, which is super important on really wide looms. It also makes the final beat-up more powerful. But there's always a trade-off, right? That higher ratio means everything has to speed up and slow down faster, which puts a ton of stress on the machine's parts. It's this constant engineering puzzle, a balancing act between speed and just not breaking.
So when you think about it, from its simple, basic parts to the incredibly complex engineering that fine-tunes its every move, the loom is just a work of mechanical genius. It's amazing that this technology, with roots stretching all the way back to ancient times, is still the foundation of so much of our modern world. It really makes you wonder, though, with all the electronics and robotics we have now, where does this ancient art go next? What will the next generation of this incredible machine even look like? And what kind of amazing new things will it create for us?